Good afternoon, everyone. Can you hear me? Okay, excellent. Okay, so because we have our exam on Wednesday, I thought I'd use today's lecture to do a review. I was originally planning on continuing the material on real-time scheduling, after we get done reviewing, but I think with the exam on Wednesday, it may be tough to focus on that. So I'm just going to review today. We plan to assign the next programming project this week, probably on the latter part of the week, Wednesday to Friday, and then in Monday's lecture I'll talk about it. Okay, so let's get started here. I'm just going to run through, hopefully you can see my slides here. I'm going to run through the interfacing and the control theory material. I'm going to go pretty fast, but if you have any questions, send a message and then I'll answer. So if there's anything unclear, let me know. Okay, so the first thing we talked about was programmed I/O, which is one of the ways that the CPU can communicate with peripherals, probably the main way, primary way. And the idea is that the CPU, or rather each peripheral, has a range of addresses, of consecutive addresses, that the CPU can load from or store to communicate with the peripheral. Obviously, in this case, the CPU is the entity that initiates this read or write operation. The peripherals can't initiate that, which is why there's interrupts, which are a way for the peripheral to get the CPU's attention. But basically, these read and write operations are done to, instead of memory words, they're called I/O registers. So when the CPU wants to talk to a peripheral, it reads or writes to an I/O register. Sometimes they're called status or control registers. And this allows the CPU to pull the state of the peripheral and to also to give it new instructions or to set bits that would make the peripheral behave in a certain way. So on the make sure that you understand that and that you can calculate the address space for peripheral. So for example, in this case, there's a USB peripheral. It starts at address 100 in hex, and the other end of the range of addresses assigned to that peripheral is 1FF. So if you want to know, for example, the total space used by that peripheral, total address space, then you can just subtract the two values, 1FF minus 100, which gives you 0FF, and then you want to add 1 to that because the addresses are inclusive. So make sure you're clear with that. Then we talked about bit twiddling, how to set specific bits and how to read specific bits within a variable. Now these variables are meant to represent control and status registers. But usually in the questions, I just refer to the values that you're bit twiddling as variables. So for example, if you want to set a certain bit to 1 in a variable, then you can set a temporary variable to 1 and then shift that value to the left by the bit position that you're interested in, which in this case is 2. And what you're doing there is setting up a you're setting up a temporary variable that you can use to kind of merge into the original variable. So we got a variable here called val, and there's this temp, which we've maneuvered this 1 bit in temp into bit position 2. Now remember, the bits are numbered from right to left starting at 0. So the rightmost bit is 0, and so bit 2 would be the third bit from the right. And then if you do a bitwise OR, the bitwise OR kind of merges two values together. So that 1 bit that we've maneuvered into bit position 2 in the temporary variable, once you OR it with val, it will effectively ensure that bit 2 in the result is set to 1. Now if that bit was already set to 1, it will still be set to 1, and if it was set to 0, it will now be set to 1. So this is how you would turn a bit on. If the bit was already turned on, that's fine. it won't do any harm. On the other hand, if we want to set a bit to 0, it's a little bit different process. You still would have a temporary variable, or it doesn't necessarily have to be a variable. It could be an expression, like a sub-expression. But the point is, you start out with 1, you shift it 2 bits, in this case 2, because we're targeting bit 2. So we're shifting it 2 bits to the left, and then we are negating, we're doing a bitwise negate, or complement rather, I should say, bitwise complement. And the idea is that we want to set every bit in the temporary variable or in the sub-expression if you're kind of inlining these operations together, where we want to set all the bits to 1 except for the bit that we want to set to 0, which in this case is in bit 2. So the way to do that is you start out with 1, shift it 2 bits to the left, complement all the bits, and that will just make bit 2 be 0 in the temporary value. And then instead of ORing, you would do a bitwise AND. So by doing a bitwise AND, you are masking off that 1 bit that's set to 0, which is the one in bit position 2. And again, if the original bit in val was 0 already, that's not going to hurt anything. If it was 1, then it will set it to 0. So this is a way to, so in other words, the point here is that you have to be careful because the way that you set a bit to 1 versus set a bit to 0 is different. So for reading bits then, there's a few different ways to do that. One way would be to take the bit number that you want to read, in this case it's 3, and shift the value that you want to read it from 3 bits to the right, and that will put the bit that you want to read, it just maneuvers it into the least significant bit position, and then you can mask it with 1. Excuse me, you can do a bitwise AND with 1. Okay, so that'll isolate the original, the bit 3 from the value. And another option is you can take the value of 1, shift it 3 bits to the left, and then do a bitwise AND. That works too. The difference is that if you do it this way, the value that you're extracting, the 1-bit field, the 1-bit value that you want to extract, is not going to be right justified. It's going to be, still in bit 3, which is fine if you're just doing like an if condition in C. And then if you have a multi-bit field that you want to isolate, you can just shift to the right by the smaller of the 2 indices. So if this is bits 5 down to 3, you would shift by 3 bits to the right, and that would maneuver those 3 bits into the rightmost bit position, and then you can do a bitwise AND by 1, 1, 1, because there's 3 bits you want to extract. If you want to do that programmatically, then you can take the value of 1, shift it to the left by 3 bits, because it's a 3-bit field, and then subtract 1, and that will give you the 1, 1, 1, right? It's pretty neat, right? If you take 1 and shift it to the left by 3 bits, that'll give you 8, and you subtract 1, it gives you 7, which is the 1, 1, 1. So in this case, you can use, for example, a variable for the width of the bit field. Okay, so this is just a summary of how to do that, and we talked about how to do load and store in C. Oh, sorry. So loading and storing in C is done with a dereference operation for a load. So just star and the address, or star and the pointer value on the right-hand side of the expression. Whoops, if you want to load, and on the left-hand side of the expression, or I should say left-hand side of the assignment statement if you want to store. So loading is just reading the contents of an address, and storing is writing the contents of an address. Okay, let's see, and then I gave some examples about, here's a specific register value with bit fields and how to read and write into them. And then we went through some examples. I'm going to go through these pretty quickly. If you have any questions about these examples, though, let me know, and I can talk about them in detail. Okay. All right, new topic, pulse width modulation. I didn't talk much about this. This is just a way to simulate an analog signal with a digital one. So you have a periodic signal that alternates between 0 and 1 at a fixed period. The period would be measured by, for example, looking at the difference in time between two rising edges or two falling edges. I usually just use rising edge just because that's just the kind of the habit that I'm in. But you could also look at the time between falling edges. But that's the period, and then the duty cycle is the percentage of the period that the signal is high. And obviously, the percentage of time that it's low would be 1 minus that. So a 10% duty cycle would be it's high 10% of the time, low 90% of the time. And in terms of the pulse width modulation, the analog value that would be given by that signal would be 10% of the voltage of the PWM. So if it's a 5-volt signal, a 10% duty cycle would give you, 10% of that, or half a volt, 500 millivolts. Okay. And then interrupts. Interrupts are the way a peripheral gets the attention of the CPU. And basically, it's just a wire that goes from the peripheral to the CPU. The peripheral, as I mentioned with the programmed I/O, the peripheral doesn't have a lot of options for actively communicating with the CPU. The CPU initiates communications through programmed I/O. If the peripheral needs the CPU to communicate or initiate communication, it would do that with an interrupt. So it would essentially raise a wire, the value of a wire, to 1. And that gets the CPU's attention, and that makes the CPU go into an interrupt service routine, which then would communicate with the peripheral and then return back to whatever it was doing at the time the interrupt occurred. Excuse me, 1 second, sorry. Okay, so now there's a few differences. There's a couple details here that you should be aware of with interrupts. So with interrupts, I mentioned there's 1 wire for each interrupt. The wires, by the way, usually go into some sort of interrupt controller that's attached to the CPU. The interrupt wires can be interpreted in different ways. You can have a level triggered interrupt, which gets the CPU's attention whenever the level of the interrupt is logic 1 or high, for instance, or low, whatever the case may be. Or there's also edge triggered interrupts, which are which convey an interrupt to the CPU on the rising or falling edge. The difference here is that, at least in the case of the Arduino style processors, you have to be kind of careful if you don't have an acknowledgement coming back from the CPU to the peripheral. So if you have a level triggered interrupt, then you want to make sure that you don't keep the interrupt signal high longer than it takes the CPU to service the interrupt request, because otherwise you may accidentally trigger multiple interrupts. You may cause the CPU to service the interrupt twice, even though only 1 interrupt has occurred. And also, by the way, interrupts are events that happen, right? They're typically events, like a packet's received or someone hits a key on the keyboard. So if the level of the interrupt wire is high too long, it would cause, for example, a key to be registered twice, for instance. With edge triggered, it's a little bit harder for that to happen because you're looking for edges. It's an edge there that's causing the CPU to enter the service handler for the interrupt. So it's harder for you to have kind of a false alarm with edge triggered. But there's also, in a little bit heavier weight processors, embedded processors, you'll have also an interrupt acknowledged. That's a signal that goes from the CPU back to the peripheral that allows you to create a handshaking for these interrupts. So that way you end up going into a sequence where the peripheral will request an interrupt, the CPU will at some point go to the interrupt handler. The time it takes it to start servicing the interrupt depends on what the CPU is doing at the time of the interrupt. Sometimes it has to finish whatever it was doing. Sometimes, the CPU may already be servicing an interrupt. Oops, sorry. The CPU may already be servicing an interrupt at the time the interrupt happens, in which case, that would be a reason why, for instance, the CPU wouldn't be able to to service the interrupt request immediately. But anyway, there's an acknowledge that comes back from the CPU to the peripheral that tells the peripheral that the CPU has acknowledged the interrupt, at which point the peripheral drops the interrupt request and then the CPU drops the acknowledge. So that way there's no chance that there'll be any kind of misunderstanding between the CPU and the peripheral, and there won't be any chance that an interrupt will be serviced twice. Okay, so switching topics again, we started talking about interface channels and protocols. We talked about asynchronous versus synchronous, kind of a, I don't know, kind of a meaningless distinction, really. Asynchronous is just there's no clock inside the channel, whereas synchronous is a clock. The first one we talked about was UART, which is comprised of 3 wires. There's a transmit, receive, and a ground. Actually, that's not entirely correct. You don't need all 3 wires. You could just have one of you could have just a receive and a ground, then a transmit and a ground connected, depending on whether or not you want to have bidirectional communication. But you do need the ground. The ground is necessary. Now, the thing about UART is that you have to cross over the wire, so the transmit output on one chip would be connected to the receive input on the other, and vice versa. The UART is asynchronous, and both sides of the channel have to agree on a baud rate in order to communicate. The baud rate defines the bit rate of the channel, which is the reciprocal of which is the amount of time devoted to each bit slot. The baud rate is called the baud rate as opposed to the bit rate, though, because the baud rate is kind of the low-level raw bit rate of the channel. It does not tell you the actual rate at which the data flows through the channel, because there's overheads in here. There's kind of bit slots that we have to use for the protocol, and we don't use for data. Specifically, that would be the start bit, stop bit, and parity bit. And there may be more than one stop bit too, depending on the settings for the UART. One thing that is always the same, though, with UART is the bits are sent from least significant to most significant. The channel, and when I say channel, I'm talking about the individual transmit and receive lines are idled at high logic 1, and so when you want to start a transmission, you would send a start bit. Start bit is always low, so you'd set the channel to low. Now with UART, you don't need to worry about conflicts with UART. UART's a point-to-point connection, so there's only one entity. The start bit will only be sent on the transmit pin, and only one chip should be driving the wire connected to any one chip's transmit pin. I know it's kind of confusing, but basically what that means is it's point to point. So you only need to worry about, you don't have to worry about collisions or anything like that. So the start bit is setting the channel to logic 0 for 1 bit time, and then stop bit is the opposite. It's setting the channel the wire to 1 for 1 bit time, and that happens at the end. So the transmission starts with the start bit and ends with the stop bit, and then the bits are sent from least significant to most significant, and then there is optionally a parity bit at the end that happens after the value is sent, the word is sent, and before the stop bit, and that could be even parity or odd parity, and that defines it's an error detecting mechanism. And if you have odd parity, it means that the transmitter will ensure that the number of 1 bits that are sent in the data and in the parity together should be odd. Yeah, that's a good question. So UART doesn't have, it's not a master-slave technology, master-slave protocol. It's just a point-to-point protocol where you have basically a transmitting side and a receiving side, and it's in the sense that you can cross them over. Yeah, so there's no slaves in UART. Okay, we talked about baud rate versus throughput. So this is kind of a terminology thing, but I mentioned that baud rate is the rate in bits per second at which the data is sent across the channel. The throughput is typically, when you say throughput, you're talking about the usable throughput, kind of the usable data, as opposed to the the start, stop, and parity bits. So the throughput is the baud rate times the number of data bits divided by the number of data plus start plus parity plus stop bits, right? And I mentioned that UART channels can have 1 or 2 stop bits. They can have a parity bit or not have a parity bit. And I think you can even, if I remember correctly, you can even have different numbers of data bits. Yeah, typically there's 8 data bits, but you can change that depending on the setup for the channel. Okay, so here's an example of a UART waveform, or kind of a timing diagram. So this is time flows from left to right. Each one of these traces is just showing 0 or 1, indicated by kind of the line being on the bottom or the top of the row, the trace row. I don't know what you call that actually. The line. So in this case, we have 7 data bits, least significant bit sent first, no parity, and 2 stop bits. And to read this, you're just looking for, well, in this case, it's easy to read. We have these little dotted lines that show you where each bit begins and ends. So the question is just how do you identify the different parts of this? Well, the start bit is first. And then we're going to have 7 data bits, so 1, 2, 3, 4, 5, 6, 7. And then there's no parity bit, and then we have 2 stop bits at the end. So if you're looking for the parity bit, it might be best to start from the right and work your way to the left, because the parity bit is towards the end. So in this case, the parity bit would be 3 bits in from the right. So 1, 2, 3. All right. Data bits would be the second bit through the 8th bit. Here. And then one of the things that's a little tricky here is that these bits are sent least significant bit first, so we're transmitting 0, 0, 0, 0, 0, 0, right, 1. So, right, 1, 2, 3, 4, 5, 6 zeros and a 1. That's the 7-bit word that we're sending through. So it's least significant bit first, so you have to reverse that if you want to actually know what the value is. And there's 7 bits, so it's like going to be like, there's 1 is going to be 1, 0, 0, 0, 0, 0, 0, right? So there's going to be a 1 and 6 zeros. Yeah, hopefully I did that right. It says 6 zeros, right? So that would be, it would look like this. So if you read from left to right, you're going to have 0, 0, 0, 0, 4, 5, 6, 7, right? And then if we reverse that, it's going to be 1, 0, 0, 0, 0, 0, 0, right? And so in hex, this would be, we'd have to separate this, so this would be 4, 0 in hex. This would be least significant bit to most significant bit, and this would be most significant bit to least significant bit. And when you write it down, you always write it as most significant bit to least significant bit, but when you read it from the waveform in this case, you're going least significant bit to most significant bit. Okay, yeah, so that kind of maps that out. There's an example. In this case, we had a missing bit. Now, normally you wouldn't, in reality, in practice, you probably wouldn't know if there's a bit missing. Like typically in reality, the bit would be corrupted, right? You'd have a bit that would be, that would be received differently than it was sent for some reason. And so generally speaking, you use the parity to detect this. The problem, of course, with parity is that you could have 2 incorrectly received bits, and then the parity wouldn't necessarily detect the problem, right? In other words, if you have two bits that are switched, flipped. If you have two flipped bits, the parity wouldn't detect that. So the parity is only going to detect an odd number of bit errors. So that's a drawback of parity. In this case, I say what bit is missing. So we're assuming that the receiver knows that there's a bad bit, and in which case it can use the parity to fix it. So in this case, we have 5 data bits. So we have, if we look at the transmit side here, we've got 1, 2, 3 bits that are 1, not including the missing one, right? Because there's 2 stop bits over here. So there's 1, 2, 3, 1 bits, and there's odd parity. So the missing bit must be a 0, because if the missing bit were a 1, then we'd have an even number of 1 bits, and that would violate the odd parity. Okay. Then we talked about SPI. SPI is a master slave. The master initiates transactions. The slave has to follow through, meaning that the slave is expected to participate in the exchange or transaction when the master initiates it. So that's the drawback of SPI, is that it's a single master protocol. Now SPI is supposed to be kind of you shift. It's supposed to be an exchange. So every byte that's sent across the SPI is an exchange where the master sends a byte to the slave and the slave sends a byte back to the master. That's not necessarily how you want to use it, but conceptually that's what's supposed to be happening there. SPI has 4 signals: clock, MOSI, MISO, and SS. And then there's also the CPOL and CFA, which are ways to set up the channel. So the master and slave are supposed to agree on these ahead of time. How does that happen? Basically, you buy a peripheral and you look up in the documentation what it uses for CPOL and CFA, and you make sure that you set you set things up to match it. If you have 2 chips that are hardwired to certain CFA and CPOL settings and they don't match, then they can't talk, basically. There's not much you can do about that, right? So the presumption here is that you have some ability to ensure that these settings match between the 2 sides of the SPI channel. Now, how do you know what CFA and CPOL are? Well, it's actually, I think it comes across as a little bit more complex than it really is. It's really kind of simple. CPOL is just what the clock is when there's no transaction. So if you look at a timing diagram like this and you look at the value of clock before things start out, which is right at the beginning of the waveform, you can see that the clock is 0. So CPOL, the clock polarity is 0. And then for CFA, all you have to do for CFA is to check when the data changes relative to the first clock edge, whether it be rising or falling. Obviously it's going to be rising for CPOL of 0 and falling for CPOL of 1. But you just look for the first edge. So the first edge here is a rising edge, and you can see the data changes before the rising edge. So CFA is 0. If CFA were 1, then the clock and the data would change at the same time. So CFA of 0 is giving the data a head start on the clock. That's the way I remember it. So let's see. I showed all four combinations there of CPOL and CFA. Okay, so reading data from SPI. This is a little tricky. I don't personally like this part because it's tricky to figure out where these bits are. So how do you do this? Well, okay, so there's, SPI works in increments of 8 bits. So for one SPI transaction, you may have 1 byte exchanged or 2 bytes or more, right? In this case, there's 1 byte being exchanged, so there's 8-bit 8-bit times, 8-bit slots. The trick is to figure out where to read the bits from. In this case, it's a little confusing because I've got these dotted lines shown in the timing diagram, the vertical lines, the vertical dotted lines. But the vertical dotted lines are based on the way that CPUL and CFA are set up. The dotted lines are marking the rising edge of the clock, which in this case happens to be where you want to read the data. And when I say read, because like when you read the data, you want to make sure you read the data in the middle of when the data is stable. You want to try to avoid reading data when it's changing. So in this case, the data is changing on the falling edge of the clock, so I want to read it on the rising edge of the clock. So I drew my own dotted lines on the falling edge of the clock because the data is stable on the rising edge of the clock in the middle. So that way, and it's kind of easy to see that once you look at where these lines are. You can see that basically I'm just drawing vertical lines wherever the data may potentially change. Now, in this case, if you look over here where my mouse cursor is, we have two consecutive zeros with MOSI and two consecutive ones on MISO. So the data isn't actually changing there, but yet we still have this, line that kind of separates those two consecutive bits. So what's the trick here? Well, it's tricky because you don't really know. It's hard to tell where you're supposed to be reading the data because of this different configuration setting. So I think the easiest way to handle this is to look at, just look at where MOSI and MISO changed the first time, and then go 1/2 clock cycle from there, and look at the clock. So in this case, it's a rising clock. So we got rising, 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 and then look at the value of those guys on each of those rising edges. That's, I think, the simplest way to do it. But like I said, it can be tricky because if you don't have these, without these guidelines here that I've got on here, it's a little hard to figure out where these bits are. Okay, so now with UART, you don't have a clock. There's no clock, so it's I guess you could argue it's even harder with UART to figure that out. Actually, if you don't have the lines on there. So yeah. Okay, so let's see, moving ahead here. So SPI has, I mentioned there's exchanges, which is exchanges refers to the single byte operations, whereas a transaction is when you use multiple exchanges to achieve a read or write operation. The reason I emphasize the terminology is not because I'm into terminology. It's just to try to make it a little bit more clear that there's a protocol. There's SPI as a protocol, but then we're building a protocol on top of that in order to do reads or writes, because SPI inherently doesn't know what a read or write is. It's just doing exchanges, just sending raw bytes between the master and the slave. We're going to build this other transaction protocol on top of it, and since it's not standardized, it depends on the the application. So in this case, there's we're saying that the first bit of the first exchange from the master is a flag that indicates a read or write. The second bit is a multiple or single indicator, a flag, and then we have 6 address bits. And then, so the first exchange is a header. It sets the thing up. And then the following exchanges are the data that either go from the master to the slave or the slave to the master. So that's really all there is to that. So you have to, now of course, when you go to read a waveform, you end up with the same problem that we had before, which is where do you read the bits? And now it's even harder because if you do a read or write, you're gonna have to do at least 2 exchanges, which means at least 16 bits. And so now you got to pick out where the 16 bits are in both the MOSI and the MISO lines. So that can be a challenge. But again, if you draw your lines on there, you can see where they work out. or where the bits are, where the bit slots are, and then you're just looking for whether MISO and MOSI are 0 or 1 during each one of those slots. SPI can be least significant bit first or most significant bit first, so that would be something, another setting, obviously. So there's actually 3 bit settings for these channels. There's CPOL, CFA, and LSB first or MSB first. Okay, so yeah, just move ahead here. Okay, and we talked about shared connections. So what if you want multiple slaves? You can only have one master, but you can have multiple slaves. There's different ways to do that. You can have them. You can have the slaves independent on their own slave select lines, or you can have them daisy chained, where each slave passes its MISO value to the MOSI of the next slave down the line. The problem with daisy chained is that it takes to do a transaction on daisy chain takes more cycles potentially. Well, I think it would always take more cycles, right? Yeah, than having a single slave. Whereas the downside of the independent approach is that each one of the slaves are all sharing one MISO line. They're basically shorting together all the MISO lines. They're being shorted together. And so that could potentially be an issue if more than one slave tries to send data on that line. Now, that's probably not going to happen, though, because the master is going to be careful to only assert one of these slave select lines at a time. So as long as the slaves have the ability to cut themselves off of the MISO line when they're not being addressed by the master, then it's not really a problem. And so I talked about that as well, where you would, to do that, you would have to have some sort of electronic cutoff. The slaves would have to be able to cut their MISO connection off, right? And the way they do that is through a tri-state buffer. All right, let's see. So the next topic was the open drain interface, which attempts to solve that problem by having each device that can potentially send a bit on a shared wire have a pull-up resistor to the power supply, and then they only pull down. And so, what's really going on? What is the advantage here? The advantage here is that the pull-up resistor ensures that you can never sink a whole lot of current because you've got a resistor that's in series with the power supply. That's good. For option 1, does each slave need a separate ground, or could all slaves be connected to a single ground? There needs to be, they all have to be on the same ground. And that's something that's confusing here, actually. I just realized that. So I mentioned that UART has a ground wire, but SPI doesn't have a ground wire as part of the channel, right? But in fact, it would have to, right? Because whenever you do any electric communication between different devices, they need to have a common reference for, at least when doing single-ended signals, when you have one bit per wire. Now, high-speed interfaces like PCI and DVI and HDMI and DisplayPort, and they have differential wires. So they have 2 wires per bit, and so the reason they have that is because the potential between those 2 wires can be positive to send a 1 and negative to send a 0, and so that way they're sort of self-referencing. And the other advantage of that is any noise that affects one wire would affect both wires equally. And so you end up, when you take the difference in voltage of those 2 wires, you cancel out the noise. It's called common mode noise rejection. But we're not talking about differential links here. We're talking about single-ended, meaning 1 wire per bit. So all of the wires sent in these channels would have to have a common ground. It wouldn't necessarily have to be the same ground as other logic on the chip, but there would have to be a ground for the channel. So thank you for asking. That's a good question. Okay, so so open drain is so you have this, basically you stick a resistor in there, so you limit the amount of current that you can sink from the power supply, even if two devices try to both put a 0, for instance, or if there's a conflict. So this bus, this type of connection would be basically logic 1 all the time when no device is sending a bit. And then each of the drivers would only have to worry about setting it to 0 at the appropriate time. The problem is that if two devices send 0 at the same time, it's hard to tell that there's a conflict. So you have to be, you basically, the only way to solve that is through the protocol. And that's the reason why I2C has this fairly strange way of doing start bits. It uses start bits. It sort of, instead of a start bit, it's kind of a start condition. So specifically, start condition is when you have, when you pull the data line from 1 to 0, so you pull it down. And when I say pull it down, I mean, set it to 0. That's step 1, right? And then step 2 is you pull the clock down, right? So why so complicated? Well, this is a way that this is all designed to be able to detect collisions on the bus, essentially. So the start condition is pull down the data, SDA, pull down the SCL. And in I2C is only the 2 wires, SDA and SCL. It stands for S data, or serial data, and S clock, or serial clock. The idea is that the start and stop signals happen when the data changes when the clock is high. Because when you send the data bits, you only change the data signal when the clock is low. Okay, so once you pull the clock down, you kind of, that's sort of the time when the data bits would transition. So as a result, this is not an edge-based signal. This is a level-based signal where you're looking at the level of clock. When the level of clock is 1, then you're reading, the value of SDA while clock is 1. So it's a little, confusing in that sense if you're used to looking for edges in these timing diagrams. The other thing that's a little confusing is that you can't tell from the timing diagram who's controlling each one of these wires. So in the case of SPI, you know that the master always controls the slave select, the clock, and MOSI. And the slave is only controlling MISO. So that's simple. Whereas with I2C, you don't know who's controlling what. And not only that, but different entities control the same signal at different points in the transaction. And there's no way to indicate that on the timing diagram. Maybe if you color coded it or something, but normally you don't do that. So you have this idea that you send, the master initially has control of both, and then the master has to yield control of SDA for only 1 bit time for the acknowledge, which is the 9th bit sent. And then likewise, whoever's controlling the data during the data portion would have to give up control for the acknowledge, the 9th bit of the data portion. So there's 2 phases happening here, basically 2 steps. One step is we send the address and the flags, and then the acknowledge for the address and the flags, and then there's a second phase where the data is conveyed, and then there's a corresponding acknowledgement for that. The problem is that when you do a read, the master controls the data initially, and then it switches control to the slave for acknowledgement. Then the slave keeps control of the data, so it could send the value back, the data that's being requested, back to the master, and then the master takes control again for the acknowledgement of the data. Whereas with if you're doing a write operation, the master sends the address, it gets back the acknowledge, then it sends the data, and it gets back the acknowledge. So on a write operation, the control of SDA has to be yielded 1, 2, 3 times, right? Whereas with a read operation, it only has to be yielded twice, right? Once for the address acknowledge, and then once for the data acknowledge. So that's kind of confusing, I think, because it's hard to tell where this change of control is happening if you're just looking at the timing diagram. So yeah, I don't really like that, but that's I squared C. Okay, so oh yeah, repeat the 3 for the write. Oh yes, so the write, yeah. So when you do a write, the first thing that happens is the master wrangles control of both the SDA and SDL. Now remember, the master always controls the clock in I squared C. So the master is controlling the clock, even though the slave may have, may need to be, sending data back to the master. So you've got the slave is being clocked by the master. Okay, but the data line, SDA, so the master starts out with control of SDA, sends the address, then yields control to the slave for the acknowledgement. So the slave acknowledges the address. So that's one change of control. Okay, now if you're doing a write operation, that means the master needs to get control again of the data so it can send the data. Because whenever you write, you have to send an address and data, right? If you do a read, you send the address and you get back the data. So if I'm doing a write, the slave wrangles control of SDA for the acknowledgement of the address, then the master wrangles control for the data, and then the slave wrangles control again for the acknowledgement of the data, right? So there's three changes of control of the SDA. And when I say control, I mean, the entity that's actually sending bits on that wire is the one that's controlling it, right? So the idea is, you want to have one entity sending bits and the other one listening. Of course, that would require that these bits these actual wires are both inputs and outputs on the chip. They're bidirectional inputs and outputs in order to implement the I squared C bus. Hopefully that answered your question. Okay. All right. And then we talked about JTAG. JTAG is kind of like it's similar to SPI. It's a serial interface. It's used for designing, testing, and debugging. It's comprised of a test data in and test data out, which is, you could think of that like MISO and MOSI. And then there's a clock, which is kind of like S clock. And then there is a test mode select and a test reset. So this is a little different because you'll notice that there's no slave select here as there is in SPI. And also there's no like start and stop bits. So the way this works is that the master, so you'll have a master that's using the JTAG, and you'll have things on the JTAG chain, devices that are being controlled. They're all seeing the same clock signal, right? So you take the clock, and the clock gets fanned out to everybody, as does the TMS. And when I say fanned out, right, what I mean by fan out is I'm using that to distinguish from a shift register style connection like TDI and TDO. So TDI comes into a chip, TDO comes out of the chip, goes in the TDI of the next chip, comes out of the TDO of that chip into the TDI of the next chip. So you have basically a daisy chain with JTAG, like you have with daisy chain, SPI daisy chain. So that's a daisy chain connection, whereas a fan out is when you have one wire that's connected to all of the devices, and so they all see the same value of those wires at the same time. Okay, so that's important to understand that, because in order to do a read or a write with JTAG, you have to use the TMS along with the clock to put these devices into the appropriate mode. Okay, so the mode, the way that's done is through a state machine. I didn't talk too much about this. We may end up having a lab on this, but the idea is that you're going to send a sequence of bits with TMS, and you clock them. And all the things on the JTAG chain sees that sequence of bits. Now that bit pattern can be used, the bit pattern that you send on TMS can be used to go to go through a 16 state machine that will put all of the devices on the JTAG chain into one of 16 states. There's two of those states, though, are the important ones, which is shift data register and shift instruction register. And so you use TMS to manipulate everything on the JTAG chain to be in one of these states. And once you get into that state, then you use the shift register to shift bits into the chain, which can be shifted into the instruction register or the data register, depending on what state you're in. An instruction register is really the address. So that's essentially how you're addressing. And you send an address by shifting in the instruction register, and you can then read or write data by doing shifts when you're in the data register state. And that's all. So basically, you switch states with TMS, and then you do your data with the TDI, TDO. That's basically how JTAG works. It's kind of neat how that works. It's different. Okay, and then I mentioned there's a few other protocols that are based on I2C. There's CAN and there's I2S. And then we compared them. So let's see, just to quickly compare them, I2C is half duplex, SPI and JTAG full duplex. I2C is the open drain, SPI and JTAG are pool. Word size with I2C is 8 bits, SPI and JTAG no restriction, addressing, there's acknowledgement in I2C. One thing I should have put in here though is the bit ordering. The bit ordering in I2C is always the same. It's most significant bit to least significant bit, whereas with UART, oh, I don't have UART on here. That explains it. Yeah, I don't have a column for UART, but UART is the bit ordering is always least significant to most significant with SPI. Sorry, with I2C, it's most significant to least significant, and with SPI could be either, depending on the demands of the protocol. Okay, that's it for interfacing. Any other questions about that? Okay, so the questions on the exam will be similar to the ones on the quiz. So there are actually 2 quizzes that we have for the interfacing chapter. Okay, now I'm going to run through control theory and just review that. Make sure everyone's comfortable with that. So let's reshare. Okay, so control theory. This one's a little bit more math intensive. We talked about what control systems are and why we need them. So control, now just to clarify this a bit, control, when you have controllers, active controllers, you can design them in a number of ways. In this chapter or this lecture, I'm focusing on linear time invariant systems. There's other ways that you can describe control systems and plants, and also designing controllers. The LTIs are simple. They're used. I mean, they're still very commonly used. But an LTI is a good way to model the behavior of a physical system, because it's basically a differential equation. So the problem, though, as I mentioned in the lecture, is that when you design a controller for an LTI, you typically design the controller also as an LTI. Well, that's a problem, because you can't actually implement a controller as an LTI because LTIs are continuous and controllers are discrete because they run on computers. Computers are discrete. So that's a challenge that you have to understand as well. Now, can you make a continuous controller? Yeah, you can, but it would have to be based on analog electronics or potentially like it could be based on heat. Like you can have a thing that heats up and changes shape, or and controls something else. Or it could be based on fluid, where you can have fluid going into something and it raises a plunger up, and kind of like how a toilet works, right? It's an analog controller. So there are analog controllers, but if you want to implement a controller on a CPU, you have to be aware of the fact that it's not continuous, it's discrete. Okay, so what is an LTI? It describes the dynamics of a physical system. It involves signals that are functions of time, and it is linear in the sense that you can have signals that can be multiplied by coefficients and added together. But you can't multiply two signals together. You can't divide signals. You can't, that kind of thing. It has to be linear. So this is an example of one here. You can also take the derivative or the integral of a signal as well in an LTI signal. And then when you do that, it's convenient to represent them in the S domain, because when you take a derivative of a signal in the time domain, then in the S domain it's just multiplying it by S, whereas if you take the integral, it's multiplying by 1 over S, or S to the minus first power. And then a transfer function is when you take, and also to be clear here too, and this, I'm not sure how well I described this originally. So S, when you take S and you multiply it by, you want to take the derivative of a signal, and then when you go to the S domain, you're taking S and multiplying it by that signal, right? So for example, SYS is the derivative of Y, whereas if you have SUS, that's the derivative of U, right? But then when you come up with the transfer function, you're kind of splitting the signals away from the S's. How do you do that? Well, you kind of factor them out. And then the transfer function is a ratio of two S domain functions, and that ratio is described as a ratio of polynomials in S, in the S space, which is I think is pretty neat. So for example, you could have a transfer function of ys relative to us, and in this case, since the numerator of the expression on the left hand side, ys is the output and u is the input. So when you create a transfer function, there's this notion of input and output. So an LTI by itself doesn't have inputs and outputs. An LTI is just a differential equation. But a transfer function is when you transform the LTI in a way that is a ratio of two signals in the S domain, which ends up giving you a ratio of polynomials in the S of S. Okay, so that's the idea. It's that's all there is to it. So you have to rearrange, the equation basically to get the desired inputs and outputs. Okay, then we talked about stability. There's three ways to determine stability. You can measure the impulse response in the time domain. You can find the S domain poles, which are the values of S that make the denominator 0, or you can simulate the transfer function in software. The simulation is done using, a simulation algorithm. It's like a discrete event simulation. I've never written one of these before, so if you simulate it, you're just kind of letting the software do the work. Whereas if you find the impulse response in the time domain, that's something you can do by hand. And so to do that, you're basically looking at the response to the Dirac delta, which is kind of an impulse, literally just an infinitely short pulse. Why can't we do this with the step function, right? You could, but it's harder to work out mathematically. The nice thing about the Dirac delta is that in the S domain it's 1, which basically means that the impulse response is free, because every transfer function is already the impulse response if you just do the inverse Laplace transform. Whereas that's not true with the step response. The step response, you got to go in, you got to multiply it by whatever the step function is. I think it's 1 over s. I don't have it here. I don't remember what the step function is. I think it's 1 over s. But there's no extra work with the impulse. The impulse signal is 1 in the S domain, so it's like free, right? So so if you have a transfer function, as we do, and you want to convert it to the time domain, you have to do an inverse Laplace transform, which involves breaking apart the ratio in a way that we can do the inverse Laplace, which means we need to get it into the form of 1 over s minus a, or a sum of 1 over s minus a terms. And for that, we can use decomposition using this technique, and then convert it to this e to the at term, which is also called the eigenfunction. And then from there, you've got a time domain function where you can just vary time from 0 to whatever. In this case, I went from 0 to 10, and what you're looking for is just a shape to see if the shape of that curve that you get is bounded or not bounded, and that'll tell you whether the system is or the transfer function, or the system described by the transfer function, is stable. Like I said, I don't really. There's a way to do this, I think, for the step function and for the ramp function, but it's not as straightforward, because you have to construct a separate, you have to build out the transfer function for the step or the ramp, whereas with the impulse, you get it for free. So we're going to focus on the impulse response, when we work these out by hand. But if you are interested in the step, this is an example of a step response. And again, I simulated this. I didn't do the inverse, Laplace on this. This is strictly a simulation of the S domain. So you can see that, it's kind of weird. You get the step goes up, and then it results in this increasing ringing in the output that's unbounded. You can also do a sine wave response too, which you can see that doesn't end well in this case. When I put a sine wave in, it kind of blows up on the output. Okay, so I mentioned the stability. You can also look for the poles in these guys. So if you have the denominator factored, and you can find the poles, which are the values of s that give you a 0 in the denominator, as long as both the poles, or not both, it could be more than 2, as long as all the poles are in the left-hand plane, meaning that they all have a negative real component, then you're good to go. It's stable. Now you might say, wait a second, what about complex numbers? We haven't looked at any complex numbers. S is a complex variable. Where's your complex s's? Yeah, absolutely. They can be complex. The roots, the poles can be complex. We just didn't look at that in this course. We don't have any examples of that. I'm just trying to keep it simple. Okay. Right. So in this case, I simulated the step response, and you can see that I got a nice little pulse there on the output, but it converged back to 0, so this was stable. Same thing with the sine wave. Okay, and then transfer function, you can build out transfer functions by multiplying them together if they're connected in series. The question is what happens when they're connected in parallel, which is what we'll get into with the closed loop response, which I'll get to in a minute. I also talked about how to take a physical system and convert it into a transfer function, or an LTI. And generally speaking, this is going to be based on physics, just force, force equations using, the force as the kind of the units, and then, for example, y is your position in this case. And of course, y dot is velocity, y dot is acceleration. So then it doesn't have to be this way. For example, you can write a physical system model for, say, an RLC circuit where you have voltage as your units. So you just have to make sure that the units are consistent when you build these physical system models. And so in this case, I was using moving an object, and I was basically doing a friction-based model. In the quiz, I gave you a pendulum model, which was similar, except it had angle as the variable theta instead of y. Okay, so that was that. We did the step response. We found that it was unbounded. And finally, we get to the real objective here, which is to take a system that is unstable and to stabilize it with a controller. Now, of course, control is not just about stabilizing. Control is also about, bending the physical world to your will by having a set point, which in this case I'm showing as RREF. So the idea is I want to take the physical system and I want it to be at RREF, and RREF is also a function of SY, because RREF is also a signal. I can change the set point as much as I want. It doesn't have to be a DC. It doesn't have to be a constant, right? It can be a signal in and of itself. But the point is that I want the output of the physical plant, the GP, which is the plant is the device I'm controlling, to be at the set point, and I'm going to use a controller to achieve that. And I have this feedback where I calculate an error term, which is the difference between the set point and the output of the plant, and then the error is the input to the controller. And then the controller has an input to the plant, which is, well, it's whatever, depends on the application. In the case of this example, the output of the controller was a force that I was exerting on an object that I wanted to move. But if this were a drone, for instance, the controller would be putting out basically a signal to the rotor, for instance, to dictate the speed of the rotor, to make the drone fly up or down, or or some other control input, right? Okay, so in this slide, I derived the signal here, and I derived the closed loop control equation. Sorry, got distracted there for a minute. And basically, the idea is that it's the open loop control divided by 1 plus the open loop control. Okay. And so that's it. We have the, then we talked about the PID controller. Excuse me one second. Sorry, someone's calling me. Okay, where is that? Okay, I'm just gonna, yeah, sorry about that. Okay, so let's see, we've got, switch back. Okay, so PID controller, there's a proportional derivative and integral constant, Kp, Ki, Kd, which are just multiplied by the air signal, the derivative of the air, and the integral of the air. Different techniques for tuning these parameters based on the application, and we won't get into those. You talked about those a little bit in your robotics class, hopefully. But we can represent the PI controller in the S domain, and we can represent the plant, obviously, in the S domain. And so if you multiply those together in the S domain, you get the open loop transfer function, and then we can calculate the closed loop transfer function using the closed loop transfer function expression. And then we can figure out from there if it's stable or not. Now, in the case of the PID controller, we don't know if it's stable. We only, because the stability will be determined by what we select for the integral, proportional, and derivative constants. So in this slide, I showed you how to do that. In this case, there's, it turns out that it's an underdefined system. Underdefined? Yeah, underdefined. We have more variables and equations, right? So we tried to pick values that would stabilize the system, and so basically, and also we wanted to pick them so our poles would be in the left-hand plane. So really, what we're doing is pole placement. This is one strategy for building controllers, is pole placement. Pole placement is fine, except it's not a just getting the poles in the left-hand plane is not often is not enough. You also want to be able to massage them so they're not only stable, but you get the desired control characteristics as well. You may want to minimize cost or whatever. There's other ways to do that. We're not going to cover those in this class, but we just want to make sure we can stabilize it. And also we manipulated some of those parameters to get different rise times and overshoots. So I talked about that. And then finally, last topic, discrete control. I mentioned that if you want to create a discrete controller, you have to do it in the Z domain. And so the Z domain is like the S domain, except it's kind of funky. Specifically, the stability criteria for Z domain is not quite as clear as with S domain. Specifically, what I mean by that is that you're not looking for the poles. It still has poles. It's basically the values of Z that will, give you a divide by 0. But the poles are not necessarily, they don't have to be in the left-hand plane for a stable system. They just have to be within the unit circle. If they're on the unit circle, then it may be stable or may not be stable. But generally speaking, you want the Z domain poles to be as close to 0 as possible. So we talked about, the differences there. And then we talked about what the Z domain is all about and how you go between Z domain and time domain. Actually, I think we covered both, right? I mean, we talked about how for the Z domain, you can go from at least integral and derivative. You can go from time to Z domain fairly easily using the first difference, which is the derivative, and then the integral is the integral Z over Z minus 1. And then if you want to go from the Z domain back to the time domain, the one way to do that is to you can calculate, well, we could do that for the transfer functions by expanding them out to where you have your signals multiplied by values of Z, and as long as those powers of Z, I should say, as long as the powers of Z are 0 and less than 0, then you can directly translate that into samples of the corresponding signal that you're multiplying Z again. So for example, Y of Z to Z times Z to the negative second power in the time domain would be Y of T minus 2 samples ago. Now you might say, well, what's a sample? What's the sample time? Well, in the Z domain, you don't necessarily have to specify the sample time. However, if you're going from the S domain to the Z domain, you do, because remember the S domain is continuous. So if we're going to if we want to convert the S domain to the Z domain, the way you do that will depend on what your time sample time is, your sample frequency, which in this case is T, and so that's part of the Tustin transform. And so we talked about the Tustin transform, which is where you substitute in S into back at 2 times Z minus 1 over T times Z plus 1 back into the S domain. Okay, so basically this is just a bunch of math. You can go from S domain to Z domain using the Tustin transform, and then once you do that, you can then kind of multiply it out, so then you can convert it back to the time domain. And why would you do that? Well, because once it's in the time domain, you can write code. You can write a simple loop that actually implements the controller, which if we were in the lab, we would be doing that, writing code and having an Arduino control something. But in this case, we're just going to kind of work it out by hand. And I had some examples here that showed actually simulated the Z domain, which you can see that it's all blocky because just because of the sample time was 1 second versus the time scale of the simulation, which was 40 seconds in this case. So so it looks kind of blocky, but I did that deliberately to show that it's discrete, basically. So yeah, that's it. That's everything we've covered so far in the course. And of course we had the lab too, which was the kind of the applied part. But this is all the material we'll have in exam 1. There'll be 15 questions. You'll have 75 minutes to answer those. So you'll have 5 minutes per question. It's multiple choice. just like the quizzes were. Yes, there will be no real-time scheduling on the exam. I did introduce that in the last lecture. We'll continue to talk about that next Monday, and then we'll move on to, after that, we'll talk about queuing theory. So yeah, that's it. Any other questions? Yeah. Yes, the exam will be on Dropbox. It's actually already on there. It's scheduled to open at midnight on Wednesday, the 24th, and it will be open until 11:59 Wednesday night. Yeah, it'll be multiple choice. That's right. And you'll get the you'll get your scores after it closes. Just so obviously, so it's 75 minutes to take it, 15 questions. The questions will be very similar to the ones on the quizzes. There'll be, it's variations on them, but make sure that you're familiar with those. Okay, well, great. If there's no other questions, then I'll go ahead and end the JTAG. There can be questions on JTAG, yes. So make sure that you're familiar. I'm not going to go into, if I have a question on JTAG, it won't be very, it won't ask you to put the JTAG devices into a certain state. I was planning to save that for a project, but just be familiar with the basics of JTAG. Okay, good. All right. Well, thank you. This lecture will be up on the Blackboard and on Moodle, and we'll see you on Wednesday. Thank you.